If you haven't yet, please get your stuff out. Find me this page. Okay, let's see how today goes. Yes, sir. You need to find the looks like this in that white box right there. Okay, so energy. Josiah, put your phone away. You guys have a fair amount of it, it would seem. Angel and Malik and crew and Lamise and crew and Himparis and crew. I haven't said shut up, but. Oh, but I wasn't. I didn't say that. Okay. I'm just going to go. Let's just do it.
Silence!
Okay, so this is the conservation of energy. Law of conservation of energy says that energy is neither created nor destroyed, but it is transformed from one form to another or transferred from one object to another. It has to go somewhere. It has to do something. And total energy before has to equal the total energy afterwards for the entirety of the system. Now, it might look like energy has been lost, but that's just if ever you're looking at something and the energy's been lost, you're just not looking at a big enough picture. The energy always has to go somewhere. Yes. So let's say that you've got potential energy. We talked about a couple forms of potential energy, but I've got spring potential energy, let's say. So I've got spring potential. I've got a rubber band here. I'll pull the thing back. I'll point it at Himparis, and I'll launch it through the air. And I missed. But there was a certain amount of potential. You shoot it back at me, Himparis. You also missed. You're better than I did, but you also perfect aim. Just you were short. So there is a particular amount of potential energy that goes into stretching the spring, and there's a particular amount of kinetic energy and a change in gravitational potential energy because it went up and then it came back down. It started at a particular level and dropped. It started not moving, but then ended moving. It reached over by Himparis at some velocity. So there's always a relationship between the amount of energy that started and the amount of energy that's available at the end. And if you're looking at the system entirely, these two values have to be the same. There has to be a complete conversion from one to the other. And if there's not, you're missing something. So let's say you've dropped an object. You drop an object off of, I don't know, a really tall building. Empire State Building is the classic example. You go to the Empire State Building and you drop a dime off the Empire State Building just down to the street below. And the thing falls and it falls and it falls, and we can measure. We know how high the thing was dropped from. We can measure the velocity at the end when the thing hits the ground. We can figure out how fast it went at the end. And if those law of conservation of energy says those values, beginning and end, need to be the same. If they're not, what is a possible reason why those two values aren't the same? Air resistance is a big one. What does air resistance do to an object? Sorry? Who said that? Josiah, was that you?
No.
Dennis?
Someone asked that.
I'm pretty sure you were right. Say it again. What does air resistance do to an object? What does air resistance do to an object?
Adds resistance to the object.
But what does it do?
Slows it down.
Okay, think of the most extreme example I can think of is this: a rocket re-entering orbit, or sorry, coming out of orbit to land. What happens to those spacecraft as they enter the atmosphere? They get crazy hot due to the air resistance of the object. So air resistance functions as a way, Harbir, Himparis, Malik, Soham, to speed, like, as an object is speeding up, air resistance is going to make it hotter and hotter and hotter. There's friction between the air molecules and the objects that are moving fast. If you ignore the heat, it's going to look like energy has disappeared. But it's got to have gone somewhere, into either the heat being produced or the sound being produced as the object moves through the air. If energy has disappeared, you're just not looking everywhere enough. In chemistry, we learned about the law of conservation of mass. Matter is neither created nor destroyed, just transformed into different forms. That's how we started balancing chemical equations. The same is true for energy. There's actually one that relates energy and mass together. You can convert mass into energy. Does anyone know the equation that does this? E equals mc squared. So if we take the law of conservation of mass and the law of conservation of energy, and you stack those two together, you combine them with this equation, E equals mc squared, the famous equation that if you just want to look or sound smart, you just toss that equation down, like, oh, look, me. I know about a guy named Einstein. What this equation actually does is it creates a relationship between the mass of an object and how much available energy that object has if you were to convert all that mass into energy. So we've got all sorts of conservation laws that exist. Okay, the faces look great. The makeup, you look great. You look great. Okay, transformed versus transferred. When energy is transformed, it changes from one form to another. So chemical to electrical, like a battery. There's a transformation of energy here. Or electrical to radiant and heat. The electricity flows through the electrons are moving through the wires. The electrical kinetic energy gets transferred into either radiant energy or thermal energy. That's a transformation. When energy is transferred, it stays in the same form, but is passed from one object to another. An example of this might be like playing pool. One ball was moving, it smacks into another ball. The first ball stops and the second ball now starts. It's been a transformation of kinetic energy of the first ball into kinetic energy of the second ball. The energy is the same. It's just been moved from one object to the next. Yes, Malik. Okay. You just made eye contact and okay. Well, moving on, for example, yeah, and the example is here. A moving object transfers its mechanical energy to a stationary object to move it. Bowling, pool, baseball, like most of sport is related to these ideas here. And there's all sorts of physical quantities that can affect different forms of energy as well. Physical quantities like mass, height, or height, mass, speed can affect different forms of energy. The higher the object is above the ground, the more gravitational potential energy it has. Conversations that we had last week. There's some more examples on the next page. Flip it over. This is what we talked about already, but we'll formalize it here. Which one of these first two pictures has more potential energy? The second one. This is the more. Which one has more potential energy here? The first one is higher up. And again, the question is always, which one would hurt more if you allowed it to hit you? This one would hurt more. This one would hurt more. Which one of these two cars would hurt more?
First one.
First one. So it has more energy. And so we talked about this last week, but we'll formalize it here too. What physical quantity can affect the mechanical kinetic energy? Well, what's going to make these things hurt more? Mass, not acceleration. Speed, but we're not going to call it speed. What's the other word for speed? Velocity. Mass and velocity for a moving object. And again, I gave you this example last week with me and my son. The more massive the object is, the faster the object's moving, the more it's going to hurt. Therefore, it's got more energy. If you're talking about gravitational potential energy, we talked about this too. Which physical quantities are going to have effects on gravitational potential energy? I walked over, I can't remember who it was, but I held objects above someone's head. We're going to let them go. Which circumstances would result in those objects hurting more? The height at which they're dropped from, the mass of the object being dropped, and gravity. How much gravity is present where you are? We said the same thing for the spring. Let's add question 3 down here. What about springs or elastics? Yes. I don't know where they are. Uh-oh. Oh, I just didn't reach down far enough. No, you're good. What about springs? What quantities that we discussed last week change how springs interact with potential energy? The length that's been extended, yeah. Length of extension or compression. And sorry? That is the same, that is this. Either how far you pull it or how far you compact it. And not how hard it's pulled, but how hard it is to pull. How hard it is to pull. This concept we talked about last week, this is called the spring constant. What is the value for the strength of the spring? The higher that value, the more energy the spring possesses. We could do a bunch of math today, but I don't really want to. We are today we are going to look at different ways of transferring and transforming energy. So, how many do I have here today? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay.